Okay, welcome everyone. Let us start our afternoon session. And the first talk by Anton Zabrodin, who will talk about Deformed Ruijsenaars-Schneider model, integrability, and time discretization.
I would like to thank the organizers for the invitation, and I will speak about the Deformed Ruijsenaars-Schneider model. This is a new integrable model, which is one parameter deformation of the Ruijsenaars-Schneider model. You know, there is a famous Calogero-Moser many-body integrable system, and Ruijsenaars-Schneider is one parameter deformation or relativistic extension of the Calogero-Moser model. There is a new parameter, velocity of light, in this model. And it turns out that this Ruijsenaars-Schneider model admits further deformation with another parameter. And this model we call deformed Ruijsenaars-Schneider model. This work was done in collaboration with Igor Krichever. It was his last work. And also partially this work was done jointly with Vadim Prokofiev. So here is a plan of the talk. I will start with main results because the main result is just equation of motion for this deformed Ruijsenaars model. And also I will show you integrals of motion, the full set of integrals of motion. Then I will pass to Ruijsenaars-Schneider model, remind you the main facts about this model, and then discuss the deformed Ruijsenaars-Schneider model and its integrals of motion. All integrable many-body systems admit time discretization when time becomes discrete with integrability, with preserved integrability. There is such time discrete versions of Calogero-Moser, Ruijsenaars-Schneider, and of this deformed Ruijsenaars-Schneider model too. There is a version with discrete time, and I will discuss it. And finally, I give some conclusions and list open problems. Integrable many-body systems plays a very important role in mathematical physics. The main examples are Calogero-Moser and Ruijsenaars-Schneider models. These models exist in rational, trigonometric, and elliptic versions. So the interaction is between particles is described by rational, trigonometric, or elliptic functions. And the most general is elliptic version because all other can be obtained by some degenerations when one or two periods of the elliptic functions go to infinity. And we will consider elliptic model as the most general one. So we need elliptic functions. Here is some definition of Weierstrass sigma function. It is defined by such infinite product. Omega 1 and omega 2, or strictly speaking, 2 omega 1 and 2 omega 2 are periods. But this Weierstrass sigma function itself is not exactly periodic. It's only quasi-periodic, because when we shift the argument by period, some exponential factor appears in front of the Weierstrass function. So, but this sigma function is a very convenient building block for construction of elliptic functions, doubly periodic functions, as ratios of products of such sigma functions with some condition for zeros and poles. So here S is the vector belonging to the lattice with periods 2 omega 1 and 2 omega 2. Also, we need Weierstrass zeta function, which is logarithmic derivative of the sigma function, and p function, Weierstrass p function, which is derivative of zeta function with minus sign, or second logarithmic derivative of sigma function, and this function is already doubly periodic. It has second order poles in all lattice points, in particular at the origin. It is the main term in Laurent expansion is 1 over x squared. So let me remind you the Calogero-Moser model. The equations of motion are here in Newton form. This model is Hamiltonian. Dot means time derivative. And this model is completely integrable. So it has n independent integrals of motion in involution. Integrability was proved by different methods by Perelomov. It was rather direct method because the proof was in proving that all eigenvalues of Lax matrix Poisson commute just by direct calculation, and Wojciechowski by other method. The Ruijsenaars-Schneider model is a deformation of Calogero-Moser model, a kind of relativistic extension. And here are equations of motion. So you see that now the equations of motion contain velocities. And here is zeta is the Weierstrass zeta function, which has first order pole in the origin. And it is an odd function. You see that when eta goes to 0, this discrete second derivative becomes continuous second derivative. And so second derivative. So here we have Weierstrass p function in the limit. And this the limit of x dot is not x dot in Calogero-Moser model, but just 1 plus some other x dot. So this limit is quite sophisticated. Integrability of the Ruijsenaars-Schneider model was proved by Ruijsenaars. But the direct method does not work in this case. And the proof was from quantum version. He considered quantum version of this model, the Hamiltonian and all higher integrals of motion as operators, shift operators, and proved that they commute by direct calculation. And then when we tend the Planck's constant to 0, we get Poisson brackets. And it appears that to prove that quantum integrals of motion commute as operators is much easier than to prove the proof with Poisson brackets. Here is the time discretization of the Ruijsenaars-Schneider model obtained by Nichkov, Rognisko, and Kuznetsov. Let xin be coordinate of the ith particle at the nth step of discrete time. N is an integer number. And here are equations of motion in discrete time. So you see that the one step of time in one direction, one step of time in another direction, And so this is a kind of difference equation, second order difference equation. The properly taken continuous time of this equation yields the equations of motion of the Ruijsenaars-Schneider model. Remarkably enough, these equations, the form of these equations is exactly like beta equations for the nested beta ansatz for models with elliptic R matrix, generalized spin chains with elliptic R matrix with nested beta ansatz. And n is the level of the beta ansatz in applications to spin chains. This n is varies from 0 to m, where m is the rank of the group. So in that case, it takes finite number of values, and here it takes infinite number of values from minus infinity to infinity. What?
This discrete.
You mean discrete quantum version
Yes.
of this model? I don't know. Now, what is deformed Ruijsenaars-Schneider model? Here you see the equations of motion. The left-hand side consists of two parts. The first part is just the left-hand side of Ruijsenaars-Schneider equations of motion. But it is not equal to 0 in this case, but there are some additional terms which are of very strange form. They are products of ratios of sigma functions. G is coupling constant, another deformation parameter. At G equals 0, we have the Ruijsenaars-Schneider model. But the value of G, if it is not 0, in fact, is not very important, because by the rescaling of time, we can always put G equal to 1, for example. But for us, it would be more convenient to put G equal to sigma of 2 eta.
Is this deformation analogous to taking x squared to
No, there are such deformations of Ruijsenaars-Schneider model. So so to speak, the model in external field. But here there is no external field, because all depends on differences between particles. Okay, and the problem, there is some problem with the question whether this model is Hamiltonian. And all attempts to find the Hamiltonian for this system failed. So it is likely that this system is not Hamiltonian. But it has n integrals of motion, independent.
Generation to Kalogera case?
You mean what happens if to tend eta to 0 in these equations of motion?
You said G to 0.
No.
G to 0 is Ruijsenaars.
Ruijsenaars is the generation to Kalogera.
Yes.
And what is the generation of deformed?
Eta to 0. You mean this limit? It is a good question, because the answer is very non-trivial. It is equations of motion. You get equations of motion which contain velocities, and triple interaction, not pairwise, but triple interaction between particles. And these equations of motion are equations of motion for poles of elliptic solutions to BKP equation. The limit is non-trivial.
But when you say it's integrable, so if you have Hamiltonian system with n integrals, you can eliminate variables and solve it completely. But if it's not Hamiltonian, it has n integrals, then why is it called integrable?
Just by analogy. I will discuss this later. There is no Lux representation for this system, but instead it admits Monakov's triple representation, which is enough to prove that characteristic polynomial of the former Lux matrix is integral of motion. What? Huh? I will show later. We will come to this. Now let me show you the discrete time version of this model. You see that there are 4 terms. Mu is a parameter which is related to the lattice spacing in the time lattice. And you see that when mu goes to 0, we get only the right-hand side remains. And in this case, these are equations of motion for the Ruijsenaars-Schneider model in discrete time. But when mu is non-zero or not infinity, we get 4 terms of similar form, similar but different form, and this is the discrete version. And these equations were predicted by Igor Krichever few years before when they were obtained. He expected that something like this should take place, that there will be cubic equations, cubic and sigma function with 4 terms. From some arguments which I cannot reproduce. Now let me remind you what is Ruijsenaars-Schneider model. This is an integrable Hamiltonian system. X and xi and pi I are canonical coordinates, and the integrals of motion are known in explicit form. Here is the set of integrals of motion. The sum goes over subsets of this set from 1 to n of n small elements. Important particular case is I1. It is the famous Hamiltonian of chiral Ruijsenaars-Schneider model. And In, which is just exponent of sum over momenta. Sum of all momenta. One can also introduce integrals of motion with I minus n. They are, of course, dependent of the integrals with plus n, but still it is convenient to introduce them. They are given by a similar formula, and I minus 1 is looks like I1 with minus signs here and here. And what is usually called Hamiltonian of Ruijsenaars-Schneider model is the sum of I1 and I minus 1. And the limit to Kalodger-Moser model in this form is most straightforward. It is also convenient to renormalize these integrals of motion introducing this factor. And higher integrals of motion can be obtained from the spectral curve. Which this is the equation of the spectral curve, which is just determinant of characteristic polynomial of the Lux matrix. Phi n is this function, ratio of products of sigma function, and the nth Hamiltonian is residue at infinity of such of z to the n minus 1 times lambda of z, where lambda of z can be read of this equation for the spectral curve. It is an implicit function of z. If you express lambda as a function of z from this equation of the spectral curve and substitute it here, you get the nth integral of motion.
In the formula on the top of the page, you divide by sigma to the power n or to the power absolute value of n? What should
To the power n.
To the power n. So it is for negative, it would be.
Yeah, right. For examples, H1 is just J1. And for higher integrals, some corrections appear. So they are linear combinations of Ji with I from 1 to n. This is the result was obtained in collaboration with Vadim Prokofiev. We also introduce the Hamiltonians, which are sums and differences of h n and h bar n, where h bar n are obtained in a similar way with j's with minus indices. It is known that the Ruijsenaars-Schneider integrals of motion can be obtained from dynamics of poles of elliptic solutions to the Toda lattice. And the Hamiltonians Hn correspond to flows according to Toda times, higher Toda times. You know, in Toda hierarchy, there is infinite number of commuting flows. To each flow corresponds time variable, and these HNs generate dynamics. Hn plus minus generate dynamics with respect to the derivative with respect to Tn and T bar n. There are two sets of times, so-called positive and negative times in the Toda lattice, and they are just sums and differences of these flows. So this Ruijsenaars-Schneider model is the same as dynamics of poles for elliptic solutions. I already said this. And moreover, this correspondence extends to a complete isomorphism between the elliptic Ruijsenaars-Schneider model with higher Hamiltonian flows and the elliptic solutions to the whole Toda hierarchy. Now, what is the deformed Ruijsenaars-Schneider model can be treated as a dynamical system for pairs of Ruijsenaars-Schneider particles. Suppose we have an even number of particles in the Ruijsenaars-Schneider model, not deformed, and they join in pairs with distance eta between particles in each pair. So here are coordinates x1, x2, x3, x4, and so on, and the neighboring particles are at the distance eta. where eta is that parameter which enters equations of motion in Hamiltonian. So the difference between x with number 2i minus x 2i minus 1 is eta. And this effective equations of motion for such pairs coincide with equations of motion of the deformed Ruijsenaars-Schneider model. However, not all flows of the Ruijsenaars-Schneider model preserve this configuration. When we have flows with respect to hn plus, this configuration immediately destroys. But hn minus preserves it. And if we consider the dynamics with respect to the corresponding time, we get the deformed Ruijsenaars-Schneider model for less number of particles, two times less, with coordinates xi capital, which are coordinates of the pairs. Eta is that parameter which enters the equations of motion of the Ruijsenaars-Schneider model. Eta is constant.
Can these points be considered as the poles of some differential equation, or maybe differential equation?
Yes.
Like Toda.
Yes. This is equations of motion for the Toda lattice with some constraint. We call it the constraint of type B, and call this model B Toda.
Some reflection.
Some condition for Lax operators of Toda lattice. And this constraint is preserved by half of the Toda flows, only by flows tk minus t minus k.
So is it related to the Inazem system, which is type B system somehow?
Not sure. Not sure. I didn't think about it, but
I mean, you seem to suggest that there is a type B Waldrop symmetry here, and so.
Yes. B Toda, what we call B Toda in continuous limits, becomes BKP. And BKP is related to series B somehow of Lie algebras. So from 4n dimensional phase space with original initial coordinates xi, pi, we come to 2n dimensional subspace of pairs, which is defined by these conditions, that the difference between neighboring particles is eta, and there is also a condition for momenta. P to I minus 1 plus P to I is equal to something which depends on coordinates. And the coordinates in this subspace are xi capital, pi capital. And this subspace is preserved by H1 minus flow, but is destroyed by H1 plus flow. So we should put T bar 1 equal to minus T1. So we should put T1 plus capital equal to 0 and consider evolution only with respect to T1 minus. Moreover, this subspace is invariant not only with respect to H1 minus flow, but also with all higher HK minus flows of the Ruijsenaars-Schneider model. This gives the possibility to obtain integrals of motion of the deformed Ruijsenaars-Schneider model by restriction of the Ruijsenaars-Schneider integrals of motion to this subspace. And this is how these integrals of motion were obtained. Here is the main result. Explicit form of integrals of motion. They look slightly complicated. The functions v and u plus, u minus are defined here. They are expressed through sigma function. Let me show, instead of this general formula, let me show a few examples which are more clear. H1 is just a sum of velocities, like a Ruijsenaars-Schneider model. But for higher integrals, some corrections appear. So the first sum is just the integral of motion of Ruijsenaars-Schneider model. But there is also additional terms, and with higher numbers of integrals of motion, the number of these terms grows. So these are examples. Here is the generating function of integrals of motion. It is such determinant which depends on two spectral variables, z and lambda. Lambda is this additional spectral parameter which enters this function. And the equation that this r of z lambda equal to 0 defines the spectral curve. And when we expand this equation in powers of z and lambda, we get different integrals of motion. You see that there are not one term here. If we neglect this last term, we get just the spectral curve of the Ruijsenaars-Schneider model. But here we have this additional term with shift minus 2 eta. Here is the shift minus eta, and here minus 2 eta. And because of this, it is much harder to expand this determinant, because for Ruijsenaars-Schneider model, we only have to use the formula for determinant of Cauchy elliptic matrix, which is well known. Here we should use formula for determinant of sum of two matrices, and this is much more complicated. But still it is possible to obtain the general form of this spectral curve. This is what we get after expanding the determinant. J, k, and j minus k are integrals of motion. It can be proved that j minus k is equal to jk. So it is not polynomial, but it is Laurent polynomial, because there are positive and negative powers of z. And here are some properties of the spectral curve. It defines a Riemann surface, which is 2n sheet covering on the here is u lambda plane, because this is a misprint, lambda plane. Here I use the letter u for this for the second spectral parameter. I'm sorry, this is lambda. And there are two endpoints above each point lambda. And this Riemann surface is invariant under simultaneous transformations, under shifts of the spectral parameters. And the factor over these transformations is an algebraic curve which covers the elliptic curve with periods to omega and to omega prime. It is the spectral curve of the deformed Ruijsenaars-Schneider model. This curve admits holomorphic involution with two fixed points. This can be seen just from the explicit form of that Laurent polynomial. The fixed points are here. There are only two of them, plus minus 1 and eta. Now, what about commutation representation for this model? There is no Lux representation. Instead, we have the commutation representation in the form of the Monakov's triple. To write it down, we need the Lamé-Hermite function. It is almost look like the function phi, which was used before, except this exponential factor, simple exponential factor. Recall that this notation ui plus minus is this product of ratios of sigma functions. And introduce three matrices. The matrix L, which is an analog of the Lux matrix. And when the second term is absent, this is the Lux matrix for the Ruijsenaars-Schneider model. The matrix M, which is the second, would it be Lux pair? This matrix M is the second matrix, which generates the flow. But here we again have the additional term. Without this term, it is the M matrix from the Ruijsenaars-Schneider model. And also we have an additional matrix R, which is of this form. And the commutation representation is the following. L dot plus commutator of matrices L and M. It was 0 for the Lux representation, but now it is not 0, but the right-hand side is R times this L minus Z to the identity matrix. This is Monakov's kind of Monakov's triple representation. And this matrix R actually has zero trace. It can be proved using some identities for elliptic functions. It can be proved that trace of R is equal to 0. And it is sufficient to show that the determinant of a characteristic polynomial is conserved. It is the generating function of integrals of motion. When you expand this determinant, you get the expression with coefficients which are integrals of motion. Now let me pass to time discretization. It is known that integrable many-body systems of Kalodjera-Moser and Ruijsenaars-Schneider type admit discretization of time which preserves integrability. And one possible way to see this is to consider the dynamics, this integrable many-body dynamics, as dynamics of poles of elliptic solutions to some nonlinear differential or difference equations like Kadamsev-Petverashvili or Toda. The nonlinear integrable equations are compatibility conditions for some linear differential or difference equations for the wave function. poles of these solutions for the psi function, which are zeros of the tau function, are simultaneously poles of the psi function. So they are subject to equations of motion of the Calogero-Moser or Ruijsenaars-Schneider type. It can be shown that zeros of the psi function satisfy the same equations. So the idea to obtain the Backlund transformation, which is can be interpreted as a discretization of time, is to consider passage from poles of the psi function to its zeros. This is a kind of Backlund transformation which can be interpreted as a shift of time by one step. And this idea works for all known integrable many-body systems, and we will apply it to the deformed Ruijsenaars-Schneider model. So, as I already said, the equations of motion of the deformed Ruijsenaars-Schneider model coincide with equations of motion for poles of elliptic solutions to the Toda lattice with constraint of type B. And here is the first linear problem, auxiliary linear problem for this constraint Toda lattice. This is with the respect to the first time flow. There is also second time flow. There is more complicated equation, and the first equation of motion for this Toda lattice with constraint of type B contains 3 times x, this t and another t, the higher t, which enters the second equation, which I didn't write here. V of x is expressed through the tau function in this way. For elliptic solutions, the tau function is the product of sigma functions with zeros at some points xi. This xi become poles of the solutions and also poles of the psi function. We can represent psi function in this form. Here is some simple factor which contains x and t, and the main part is this ratio of two tau functions, tau with tau hat and tau. And mu is a parameter which is in fact related to the spacing in time lattice. And this function tau hat is also a product of sigma functions with zeros at some other points yi. And we assume that xi and yi are all different in general position. The zeros and poles of the psi function obey this system of equations. It can be obtained by direct substitution of the psi function in this form with this tau and tau hat to this equation. You get the left-hand side, the right-hand side, and both sides have poles at xi and yi. And you make the coefficients in front of these poles equal, and in this way you get these equations. This is a passage from xi to yi is the Backlund transformation, because xi satisfy the equations of motion of the Ruijsenaars-Schneider model, and yi also satisfy. These equations are in fact symmetric with respect to the permutation between x and y, and also eta to minus eta. And from these equations, when you say that yi is xi in the next step of time, so you denote xi as xin and yi as xin plus 1. And in this way, here is in written form, in this way, you get these equations of motion in discrete time, which are cubic in sigma functions and contain 4 terms. Mu is lattice spacing in time lattice.
What is the deformation?
Deformation parameter, it does not enter here because, as I said, it can be eliminated by rescaling of time. And in discrete time, it disappears somehow.
Can I put it in?
So these equations need some interpretation. In particular, the very interesting question is whether they are related to some beta ansatz, because, as I said, the discrete time equations of motion for Ruijsenaars-Schneider model are exactly nested beta ansatz equations for models with elliptic metrics. And this, about these equations, I can say nothing at the moment. This is an interesting question. Whether they can be interpreted in terms of beta ansatz, but it's still not clear for the Ruijsenaars-Schneider case. Is it this coincidence is just a coincidence, or there are some deep reasons for it? This is still not clear. Some words about continuum limits in time. There are different continuum limits of these equations because you can you can make n continuous in different ways. One way is to say that introduce new variables x capital, which are xin minus n eta, and say that in the continuous time limit, this x capital change continues smoothly. So x, for example, xin plus 1 is xin plus some terms which are proportional to epsilon when epsilon goes to 0. And the lattice spacing is epsilon. So the continuous time variable is t is n times epsilon. Epsilon tends to 0 and goes to infinity. So this t remains finite. When we expand in powers of epsilon, it is enough to expand up to the second order. And as epsilon goes to 0, and for consistency, we should say that mu to the minus 1 is equal to epsilon. And then equating the terms proportional to epsilon squared, we obtain, in the leading order of epsilon, we obtain equations of motion of the deformed Ruijsenaars-Schneider model. Another possibility is to assume that the original variables, xi small, behave smoothly when time changed. So we have expansion like this in this case. And in general position, mu to the minus 2 degree minus 1 is O of 1 as the epsilon goes to 0. And in this case, the leading order in epsilon after the expansion gives the equations of motion of the non-deformed Ruijsenaars-Schneider model. However, when mu to the minus 2 is 1 plus some alpha times epsilon, so this order is O of epsilon, then the first order in epsilon gives the identity. 0 equals 0. And one should expand up to the next order in epsilon. In this case, we obtain equations of for dynamics of poles of elliptic solutions to the semi-discrete BKP equation, which were obtained in our joint work with Daria Rudneva. And these equations are rather complicated. They are not, the left-hand side, the right-hand sides are not expressed as if in terms of xi2 dot. They are not of the form that xi2 dot is equal to some function of xi and xi dot. They are contain xi2 dots under the sum, the sign of sum. So they are complicated. Now, concluding remarks, we proved integrability of the deformed Ruijsenaars-Schneider system by presenting integrals of motion in explicit form. We also obtained the discrete time version of the deformed Ruijsenaars-Schneider model by considering its Backlund transformation. I should say that the connection between the non-deformed Ruijsenaars-Schneider model and deformed one is not trivial, because there are two sides of this connection. On one hand, the deformed model is an extension of the non-deformed one, because it contains it as a particular case when this additional parameter g is equal to 0. However, on the other hand, the deformed Ruijsenaars system is contained in the non-deformed one, because, as I said, the equations of motion for the deformed model are equations of motion for pairs of Ruijsenaars-Schneider particles when particles stick together, join in pairs with distance eta between particles in each pair. And the equations of motion are obtained by restriction of the Ruijsenaars-Schneider dynamics to this subspace of the full phase space, which corresponds to this configuration. I think this is all. And finally, I would say about unsolved problems in this respect. The main problem is about Hamiltonian structure of this model. It's not clear. Presumably, this system is not Hamiltonian. Related question is quantization of this system, because when system is not Hamiltonian, it's not clear how to quantize it. Another interesting question is to ask whether more complicated complexes of Ruijsenaars-Schneider particles are possible. We considered pairs when particles join in pairs, and these pairs move as a whole thing. And what about triples and more strings containing more particles? Whether there are some subset of integrable flows which preserve such configurations. This is not clear. If, by the way, in the limit to the Calogero model, this eta goes to 0, and the two particles in each pair become in one and the same point. This configuration, this can be considered separately in terms of Calogero-Moser model, to consider such configuration when particles are in one and the same point. This is rather singular configuration, and the question about the Ruijsenaars-Schneider model is to ask whether we can put two particles in one and the same point. We put them at the distance eta, but what about one and the same point? Which equations of motion we obtain in this case? So this is all. Thank you.
Questions? Please ask using microphone.
Anton, hello? The equations of motions that you obtained, these are second order differential equations. You can always make them Hamiltonian. By saying that it's not Hamiltonian, you mean the integrals, they don't Poisson commute?
No, because Hamiltonian means almost the same as Lagrangian. Because when the system is Hamiltonian, we always can write down Lagrangian and vice versa. When the system is Lagrangian, it is simultaneously Hamiltonian. But this system is probably is not Lagrangian, because there are some criteria for whether the system is Lagrangian or not. And these equations of motion do not satisfy this criteria.
Okay.
So this most probably the system is not Lagrangian and so not Hamiltonian.
Okay, but some system, Hamiltonian and stuff, but you consider a particular solution, class of solution of this system, and then then you don't see the Hamiltonian structure.
Particular solutions of what system?
So you have a Hamiltonian system, but
Yes.
consider a class of solutions. Then you don't see the structure, but the equations are okay. Could it be like that? Make some reduction, consider class of solutions.
Of course, the original Ruijsenaars-Schneider system is Hamiltonian. What happens? We restrict the full phase space to half-dimensional space corresponding to this configuration of pairs. And this subset of submanifold of the full phase space appears to be Lagrangian. So Poisson brackets between integrals of motion restricted to this subspace is 0. And the dynamics with respect to higher Ruijsenaars-Schneider flows induce some flows in this subspace. And the question is, can it be Hamiltonian or not? I don't know the answer. Is there any natural Hamiltonian structure, symplectic structure on this subspace? I doubt.
Is it not the Hamiltonian system with constraints?
Hmm?
It's not the Hamiltonian. Is it not the Hamiltonian system with constraints? Because as I understood, you can obtain this from Ruijsenaars-Schneider adding some constraints.
Yes.
And
But after putting the constraint, the system fails to be Hamiltonian.
So it's like gauge theory. My question is does there exist, if we restrict ourselves to not for elliptic but for rational Ruijsenaars? And
Sure, because you
It's-
can degenerate the sigma function
Yes,
to
it's-
sinus or just x, and then we get the same story about trigonometric and rational models.
does there exist the same deformation for corresponding trigonometric collider model?
You see, there are two different limits. We have two deformation constants, g and eta. And we can tend one or another to 0. And the limit depends on the order in which we do this.
Yes, I mean, if there is a corresponding like Ruijsenaars dual trigonometry for general rational Ruijsenaars, there exists a corresponding Ruijsenaars
You
dual
ask about duality
yes,
for
there's
this model. This is a good question.
It's
I
possible to
don't know.
deform the dual.
Yeah. What is the dual for this deformed model? Yeah, interesting. I don't know.
Maybe one last question.
What do you mean by a spectral curve? Spectral
This
curve.
Determinant of characteristic polynomial defines the spectral curve, because this is a curve because we have two variables connecting related by one equation. This is a complex curve, which usually, at least when we have Lax representation, this curve is called spectral curve, because it is related to the spectrum of the Lax matrix.
Are they always algebraic?
It is algebraic curve of finite genus, which is equal to, I don't remember now, some n or 2n, where n is number of particles.
Is it hyperelliptic?
Hmm?
This question was, is it hyperelliptic?
No.
So you said that there is some subset of the phase space which is invariant under part of the flows. Yeah? But what happens if you restrict symplectic form to this subset? What do you get? You get 0 or you get...
Zero. I say this subset is Lagrangian.
Ah, okay.
Let's thank Anton again.